Okay, so thank you so much for having me. I know that I was supposed to give a seminar a while ago and I had to postpone it, so sorry. But okay, so my name is Christina McCluskey. I am a scientist at the CGD lab at NCAR. And today the title of my talk is Ice, Ice, Maybe, Aerosol Cloud Interactions over the Southern Ocean region. Today, I'm going to talk about some of the motivation behind this, since I know this is an interdisciplinary audience. And I'm going to talk specifically about aerosol assessments and CESM, which is part of a few different publications, and then also talk about whether or not we have tools to really determine the role of aerosol in Southern Ocean clouds in our climate system. So I'll get started here. The motivation behind this is really driven by the complexity of cloud processes. This here is a cartoon showing the various processes that are active in different clouds. This is a cartoon thinking about many types of processes. We have liquid phase processes here. I think, can you see my cursor? Um, okay, great. And so here we have a lot of cloud droplet activation, collision of cloud droplets. As we get to colder temperatures, let's say 0 degrees Celsius, we can have both liquid and ice phase. And so we have different growth regimes in terms of vapor deposition, and also the actual collision of droplets onto ice, called riming. And then, of course, at the very cold temperatures, colder than -40 degrees Celsius, we have homogeneous freezing and ice processes here. So between the liquid, mixed, and the ice phases, we have different processes that would dominate. This is very complicated, as you can imagine, even if you just looked out in your window on a given day, clouds evolve very quickly. I know clouds are a complex system. And in particular, a lot of questions remain regarding how aerosol would influence these processes. So right here, there's a sort of hint at aerosol and CC and an INP. So these are the terms I'll be using a lot in this talk. The cloud condensation nuclei. So these are particles that allow for cloud droplets to activate and form these cloud droplets and then determine a lot of these processes we see here. And then ice nucleating particles, which is a whole nother area of research thinking about how particles in the atmosphere have unique sites on their surface that allow for ice formation in this mixed phase regime. So that's between 0 and -40 degrees Celsius. So those are the types of particles we're thinking about. As you can imagine, there's a lot of variability in the types of particles across the globe. This is a cartoon or a video showing that complexity where we have different biomass burning emissions, dust emissions, pollution sources. If we look over the Southern Ocean, we see a lot of sea salt, and occasionally some continental aerosol sources are coming in from different land locations. What's nice about the Southern Ocean and what's sort of convenient and why I've focused a lot on this region is because it's a little simpler in a lot of ways in terms of aerosol, whereas the Arctic, we have, of course, many complex sources that are much more variable. There is still variability over the Southern Ocean, and we'll talk about that, but in general, the Southern Ocean serves as a nice laboratory for studying these aerosol. And I just want to again motivate this by highlighting cloud feedbacks and how sensitive our climate system is to changes in aerosol, or perhaps not. We're still investigating that. So in this case, I'm going to show some results from Zelinka that looked at the climate sensitivity of these different coupled models. So CMIP is the coupled model intercomparison project. CMIP 5 and CMIP 6 are two different versions of that project. And here is showing what's called equilibrium climate sensitivity, or the magnitude of a climate response, in this case, the change in temperature, global temperature, to a perturbation. In this case, a doubling of carbon dioxide. And when we estimate the equilibrium climate sensitivity, or ECS, from these two groups of models, so you can see there are many models that participate in this intercomparison project, we see that there's overall a pretty large range in the climate sensitivity, and that range of possibilities has actually increased between CMIP 5 and CMIP 6. And when that variability in that those forcings are broken down into different components, including the RH component, the albedo cloud, et cetera, shown here, what we find is that clouds are contributing mostly to that variability. So a lot of our uncertainty is really in this cloud piece. We also know that we can run what's called PPEs. So these are where we run the model with different parameter settings. So models, of course, have a bunch of different parameterizations, and we can modify those parameters, run the model many, many times. And what that allows us to understand is that what's called parametric uncertainty versus structural uncertainty in a model, which is what CMIP is providing. And what this is showing, the study from Margaret Duffy, is highlighting that for these different cloud feedbacks, you have the same amount of variability and within a parameter set and also within a structural set. So this is just kind of highlighting, again, we have a lot of uncertainty in our climate models regarding these processes. And so again, Southern Ocean is a place that provides us with a simplified process system. This is a nice video from our Socrates campaign from 2018. And a couple of statistics, we have about 80% cloud cover annually. And most of these clouds are low level, so they're close to the ocean surface. And most of them are also mixed phase. So they're in that sort of complex range between 0 and negative 40 degrees Celsius. And so this is a nice place to study mixed phase clouds. We also know that because of this high cloud occurrence, the Southern Ocean is a really critical component of the Earth system. This was a nice study done a few years ago now, looking at 150-year simulation. And what's shown here is the calculated optical depth feedback from those clouds. And so you can see over the Southern Ocean, we have this cooling effect. And this is due to the shift as warmer temperatures lead to more liquid-dominated clouds versus ice-containing clouds. These clouds become brighter, and that results in a cooling effect. In the last 15 years of that simulation, they also looked at the same feedbacks. And what they see is that the cooling effect of the Southern Ocean is actually lower than it was in the first 15 years. And what this is showing is that there's basically a state dependence of this feedback. So that in these last 15 years of the simulation, most of the clouds are already liquid. And so you don't have that shift from ice containing to liquid, pure liquid clouds. And so in this simulation, this is suggesting that after some amount of warming, all the clouds over the Southern Ocean will become fully liquid, and this dampens the overall cloud phase feedback. So this is a feedback that we're interested in making sure we are representing correctly, because as you can imagine, this relies on accurate processes in the model. And then I just want to highlight that we still continue to be challenged by Southern Ocean clouds. This is a more recent assessment of the community atmosphere model as part of the community Earth system model, or CESM. It's a pretty widely used model. And here is looking at just the cloud cover bias compared to the satellite historical record. And what we find is that over the Southern Ocean, we actually have too many clouds in CAM6. And then there are, of course, other places where we have different cloud biases. And we also know from in situ aircraft observations and assessments we were able to do with that from Andrew Gettleman's paper a couple years ago, that when we look at basically co-located comparisons of the model and the observations from aircraft, we have the temperature pretty well captured because we're nudging these simulations. We have cloud water content that looks pretty decent. And then the ice water content here, you can see the observations have a lot of uncertainties because ice in clouds is extremely difficult to measure. But in general, we see that the model does not produce very much cloud ice compared to the observations. Excuse me. So thinking about this conceptually in terms of how we want to tackle this in terms of assessing the model, I'm going to first talk today about the aerosol piece of this. So thinking about the different sources of cloud condensation nuclei, or CCN. So these are sea spray aerosol, sulfate aerosol, and even long-range transport. And then ice nucleating particles, which there's been a lot of different measurements from different groups looking at sea spray aerosol sources and also long-range transport of things like mineral dust. So I'll talk about that. And then there's a whole lot of processes that we are trying to investigate that are sort of downstream of these aerosol. So, there's a lot of chemistry here involved in this aerosol piece, but of course that chemistry has an influence on the clouds too. So we'll talk a little bit about cloud droplet activation, autoconversion, and then of course ice nucleation shown here in this sort of mixed phase temperature regime. Okay, so what do we know so far about the role of ice nucleating particles in Southern Ocean clouds? This is a really nice study done a few years ago looking at a regional model, and this is looking at one particular case study where the shortwave cloud flux flux was estimated by satellite here on the left. And then the sort of default physics were used to simulate that case. And in this case, there were a whole bunch of ice nucleating particles in that model setup. And then they reran the model with a new ice nucleation scheme that accounted for the lack of ice nucleating particles. So basically allowing for more supercooled liquid, less ice. And you can see the improvement to that simulated shortwave flux. And this indicates that the ice nucleating particles and how the only difference between these two simulations is ice nucleation. So this indicates that ice nucleation is very important for determining the properties of these clouds. Then there are other studies that had conflicting results. This is looking now at a coarse resolution model. So this one up here, I think was like 5 kilometers or 15 kilometers, very high resolution compared to this one, which is a 2-degree model. And in this case, running the simulation and different ice nucleation parameterizations and looking at these top of atmosphere metrics. So then again, shortwave cloud forcing, long-wave cloud forcing. They also looked at ice water path and other metrics. They don't really see much difference. And so this is showing in a different model that the ice nucleating particle population has no real control over the climate. So this is, of course, driving and motivating a lot of our research is, okay, what is the way we do this, or what is the answer? And so, again, first I'm going to talk about the Southern Ocean aerosol assessments. Here I'm leveraging both models and observations, basically doing this comparison between what we observe and what we see, or what we simulate. In this case, I'm going to be looking mostly at the Marcus and Socrates campaigns. So these are a few years old now, but there's a lot more data that we're looking forward to also expanding this analysis to. For Marcus, this was a ship-based campaign. It was a resupply voyages to Antarctica. And it spans several, about 3 different seasons, which is really great. And then we have Socrates, which are these orange lines here, which was an aircraft campaign during the summertime in 2018. And during these campaigns, we had different measurements of aerosol amount and size. We had ways of determining any sort of terrestrial influence, because as I mentioned, we want to make sure we can capture that in terms of its possible sources to the CCN and IMP that we were also monitoring. Okay, and then for the model we're using is a community Earth system model. So this is CESM2. Again, this is a coarse resolution model. So think resolutions on the order of 100 kilometers, 150 kilometers, 32 levels from the surface all the way to 1 hectopascals, and a 30-minute time step. So we're looking to use a very coarse resolution model to study these cloud microphysics processes. And I see Lisa laughing. It's a really challenging thing. And what's important though is that these models are what's being used to figure out what the future holds, right? And so we do really want to interrogate these models as much as we can. The aerosol model that's used in this is called MAM4. So these modes are described here. So this is an example of the size distributions of aerosol that you would get from the model. So you can see these Aiken, very small particles, accumulation mode, and coarse mode particles. And so we specifically are simulating sea salt, black carbon, particulate organic matter, which mainly comes from biomass burning sources in the model, sulfate aerosol, and secondary organic aerosol, and also dust, which isn't here for some reason. Sorry about that. Okay, so when we're thinking about comparing models and observations, we like to think about how we could get some nice apple-to-apple comparison. But we know as people, I think, using both models and collecting observations is that there are issues with both of these. Models make a lot of assumptions in order to consider things like computational expense or even just our lack of understanding of a system. And then observations often come with assumptions or maybe some missing data or something that all of us know deep in our heart has to be figured out before we can make any science from those observations. And so our goal is really to think about how can we translate that model information into something that looks more similar to our observations, and how can we make sure we understand our observations thoroughly to be able to do that comparison. So that's what is sort of the spirit behind a lot of these comparisons, and we do our best to do so. Okay, so here's an example of deploying these in situ aerosol instruments and doing these co-located comparisons. So here we can see that our aircraft took off. We ferried down to about 62 south and then started profiling the clouds along our way back to Hobart. And so in our comparisons, what we're doing is basically collecting model data along that flight track. And then we're simulating our observations. So I'll give it an example here from the USOS, which is a measurement used to measure size distributions. What we're doing is in the model, taking only the particles that are within that size range and integrating that size distribution to get an apple to apple comparison. So here's a couple assessments I'll share. This is looking again at the USOS observations, and the model is in red and observations are in black. And overall, we see that for all the different data collected south of 45 degrees latitude, we see that the model has an overall underestimate of these particles at these size ranges. When we look at the size distributions produced from the model here in red and observations in black, we can see that the model in general has a quite a funky shape compared to what we observe, where the observations highlight this very small mode of aerosol particles down here at the very small sizes, both in the upper troposphere and in the marine boundary layer. And when we look at the composition of these particles, this is looking at 100 to 500 nanometer particles. And the observations, so these are basically electron microscopy measurements where you collect particles onto a grid, bring them back to the lab and look at their composition and also their morphology to identify what types of particles they are. What we find is that both below and above the clouds, we see mostly sulfate particles. When we do that same assessment, like I said, collecting those observations from the model, we don't see those sulfate particles. Those are missing from the model. So this is highlighting a potential lack of sulfate aerosol. And this has been looked at into more detail by a visiting student, Qing Yu, who's about to be graduating, if you have a postdoc available. But she has looked at the relative bias of cloud condensation nuclei active at 0.5% supersaturation compared to the model. And this is looking at different latitudes. And what we see is that overall, there's a low bias in the model's prediction of CCN. She was able to look at this in a little more detail, particularly over this so-called Southern Ocean, so south of 62. This is where we're getting closer to the marginal ice zone, where there's a lot of biological activity that drives DMS production, and then would, of course, be a source of sulfate aerosol. So by looking at just the November time period, so winter time over this particular latitude band, what's shown here are the CCN number concentrations at different supersaturations. By looking at CCN number concentrations at different supersaturations, we can get a hint at what types of particles are driving the CCN population. In this case, the observations are higher than the observed. The observed are higher than the model in the winter time. And this is exacerbated in the summertime, where in the summertime, the observations show this very strong dependence of supersaturation. This is a pretty obvious sign of having small particles that don't have a super high hygroscopicity. And so this is showing this like summertime source of small organic or sulfate type particles contributing to the CCN population. And again, this is highlighting that the model is not able to pick that up. What she's been able to do is then run a couple different simulations just to see if we can correct the CCN number concentration. Are we able to recover cloud droplet number concentration, or what happens to cloud droplet number concentration when we do that? And so there's going to be two simulations I'll show here. The top row will be the default model, and then the bottom row will be reducing the sea salt emission component, so that you can see her paper for more information on this, but also enhancing, the DMS emissions by a factor of 3. These are, in fact, a little bit arbitrary. The sea salt one is based on observations. The DMS emissions increase is really a kind of rough handle, but we just want to see how does the model respond to this. And what we're doing is measuring the cloud droplet number concentration, or estimating that, from ship-based measurements from JMACE. And so those are shown in black. On the left is for all of the data that's collected. In the middle here is for 50 to 55 south. And then on the right is 55 to 68 south. And so what we see is that when we have these modifications that basically improve the CCN number concentration, so the CCNs that are predicted are much better, we can see the shift from the original simulation where we had too low cloud droplet number concentrations. We can see the shift to higher cloud droplet number concentrations. So this is basically saying that as we improve our representation of CCN, the cloud droplet number concentration in the model is responding in a way that makes sense. So that's good. Um, and so this is nice moving in terms of addressing some of these biases. And we're continuing work on that. I'm going to shift gears just a little bit here to talk about ice nucleating particles. So ice nucleating particles, as I mentioned, are required for forming ice crystals and clouds between that 0 to negative 40 degrees Celsius. We have existing parameterizations for ice nucleating particles based on a whole bunch of different field campaigns and laboratory studies. In this case, I'm going to be using a pretty simplified picture of IMPs, again, because we're over the Southern Ocean, where most of our IMP we're going to assume can be described using this DeMont 2015 dust IMP parameterization and this McCluskey 2018 marine IMP parameterization. We know that dust does contribute to the IMP population as shown here in this pie chart from Tu et al. 2021, looking at the composition of ice crystal residuals. We do see these dust particles, and then of course the organics and sea spray. And then I just want to point out here too, where we used a model to determine the vertical distribution of ice nucleating particles to see when we would have sea spray dominated in blue versus mineral dust dominated in red. And you can see there's some seasonal variability. And so this is what drives this motivation of including both sea spray and dust aerosol for INP. One thing that was really nice to be able to do for the Marcus campaign was we were able to perform an observational closure study. And so what we mean by this is we're going to take this marine organic IMP parameterization, and then inside of this parameterization, we need an estimate of the sea spray aerosol surface area, which we were able to derive from our Marcus observations using a nephelometer. Again, we're over the Southern Ocean, just makes it possible to do some of these more simplified measurements. And so we can use that as input into this parameterization and compare that with the observed IMP. We were also able to compare not just the total IMP, so this is looking at IMP number concentrations as a function of temperature. The black is all the ice nucleating particles, and then we do these different treatments, including heating and also this hydrogen peroxide digestion, which basically removes all of the organics in the sample, and we're able to derive what's heat labile, what's organic, and then what's our refractory IMPs. So that's what allows us to get at the more of the IMP types. So this is kind of a busy figure, but the idea here is that we're comparing our predicted IMP number concentrations using this approach here, using that sea spray surface area as input to that parameterization compared to the observations from Marcus. And the colors of these points are all different ice nucleation temperatures from -10 to -30. And then on the left here is no treatment at all. So this is the total IMP number concentrations. And then here's on the bottom row are the heat treated. So that's removing those organic heat labile. Now, for those who are outside of the ice nucleation community, I do want to point out these are log scale figures. So but this is pretty common for our measurement type, and we can talk more about that. But one of the things to point out is basically that within an order of magnitude, we're able to predict this kind of with our closure study, and this suggests that the dominant IMP type is marine, and also provides us some confidence in using this in our model. Okay, so then now what happens if we use the predicted from the model, the predicted aerosol as input to those parameterizations? So what's shown here is now the y-axis is actually from the model. So the model is predicting the aerosol and we're feeding that parameterization, the aerosol from that model. Same type of plot looking at the agreement between these two. And we see in general that we have about 80% of our data points are predictable within an order of magnitude. But we want to highlight that this is from Marcus. So this is at the surface, which is really close to that marine source. When we go to our aircraft observations, we see a lot more variability. And what's shown here now is aircraft observations collected from 0.5 to 6.2 kilometers. So this is, a whole bunch of observations collected over different parts of the atmosphere. And what we see is a whole lot more variability. Our model in particular produces, what is this, 1, 2, 3, 4, 5 orders of magnitude variability in our IMP prediction. And so looking at that a little bit closer with the model, we wanted to see, okay, for the model at a given latitude, are we dominated by marine IMPs or dust IMPs? And that's what's shown here, where the dust dominated IMP populations are shown in these red colors, and then marine dominated are blue colors. And when we look at the agreement between our predicted from the model and observed from Socrates, we see that we have a tighter cluster overall, an under prediction of IMPs from the marine, but a tighter clustering of those data. Whereas with when the model thinks that there's dust in the atmosphere, you see all that variability. And so really the dust that's being transported over long distances is driving most of the uncertainty in our ability to predict IMP in this particular field campaign. And this really left us with kind of an outstanding question that a lot of people spend their whole career trying to answer, which is how well do we need to be able to predict IMPs, and how well how sensitive are the clouds to changes in ice depleting particles? So that's where I'm going to shift gears a little bit and think more about cloud processes. Where here we basically did a repeat of that Shao et al. Study using CESM, looking at different ways of representing ice nucleating particles. So here I'm going to show this is now a 2-degree simulation, and this is a free running climate simulation for 2 years. And the idea here is to look at the ice water path for different representations of ice nucleating particles. And what we find is that for all our different top of atmosphere metrics consistent with Shao et al., this model shows no sensitivity to changes in ice nuclei. And this was consistent. There was basically no change in ice water path, liquid water path, shortwave or long wave cloud radiative effects due to these changes in ice nucleation. So this suggests, if you take this for face value, this model tells us that it doesn't matter how well you predict ice nucleating particles. And as you can probably imagine, as someone who spent a lot of time measuring ice nucleating particles, I kind of refuse to believe that that's the case, based on what I know of these clouds and the prevalence of supercooled liquid. And so we wanted to look a little more closer at the model. And so what I'm showing here is a temperature-dependent number concentrations of different hydrometeor types. So in this yellow color are cloud droplet number concentrations. We have ice concentrations in blue. There's no snow, and then we have rain here. And then we're able with the model to look at what's called process rates or tendencies. And so both on the left and the right, these are both tendencies, whereas the left is looking at mass tendency. So how much change in ice mass due to these different processes. And then this is the change in number, what number of particles are changing due to these different processes. And what we find is that for all these are the different processes represented in the model for contributing to ice. So we have immersion freezing of cloud droplets, immersion freezing of rain, Hallett-Mossett rime splintering. There's also contact freezing, deposition freezing, and then ice sedimentation, which is a sync term. And what we find is that in terms of number, immersion freezing of cloud droplets actually dominate only at -25°C. Whereas immersion freezing of rain is actually what's driving ice formation at these warmer temperatures and then kicking off that secondary ice production process through rime splintering. And this immersion freezing of cloud droplets, that's what we're perturbing in our ice nucleation experiments. Ice nucleation is the ice nucleation of a cloud droplet, not a rain droplet. And so what this is showing basically is that immersion freezing of rain is the dominant ice formation process. So what is immersion freezing of rain and why is it in the model? Well, immersion freezing of rain, the idea is that as cloud droplets grow through their collection of other cloud droplets, large cloud droplets have a higher probability of containing an ice nucleating particle. And so once that rain droplet is super cooled or at a very cold temperature, it has a higher probability of freezing, and then you have your ice formation. So this is the concept behind the immersion freezing of rain. This is parameterized in the model using a very dated fit to Keith Biggs' work looking at the freezing dependence on the size dependence of freezing. And this is actually one precipitation sample collected in McGill, published, I think, in 1964. And so one of the reasons why this parameterization was implemented was basically so you don't have super cold rain in Colorado, for example, right? We do have freezing rain, or there's sort of places for this to matter. But this is a problem for the Southern Ocean, and I'm gonna talk a little bit more about where that comes from. When we look at emergent freezing of rain, one of our questions was, well, where does the rain come from? And so this is now looking at the tendencies, but for rain, where in number, the auto conversion of cloud droplets to rain is the dominant source of rain in these clouds. So this is a little bit of a cloud physics process, but basically cloud droplets in the model, we need to somehow grow them very quickly. And again, we have this large time step. And so this is through the process called auto conversion. This auto conversion process is parameterized right here, where you have some change in our cloud droplet mass due to and it's a function of the cloud droplet mass mixing ratio and the cloud droplet number concentration, where these exponent values are parameters that are often used for tuning. But in particular, one that is important to note is that cloud droplet number concentration is on the denominator. And one thing that we know, and I just showed some results that support this, which is we don't have enough CCN and we don't have enough cloud droplets. And this is another example of another study from Isabel McCoy, where cloud droplet number concentrations from the model and these two thinner lines are compared to the Socrates observations. What we see is that in the model, we have a lot of cloud droplet number concentrations that fall below 10 per cubic centimeter. These are extremely low cloud droplet number concentrations, and that really drives this rapid auto conversion process. So basically, I have a kind of cartoon to try to summarize this, but the idea is that we have this low bias in cloud droplet number concentrations. And I do want to point out, this isn't just CESM. This is, and there are a number of models that struggle with this type of bias over the Southern Ocean. This is looking at pre-industrial and present day simulations from the different Aerosol models. But this low bias in cloud droplet number concentration is likely driven by both low biases in our cloud condensation nuclei, so that's that sulfur chemistry, that missing sulfur aerosol, and also subgrid turbulence is something that we're also looking at. But this low bias in cloud droplet number concentration really drives the formation of the supercooled rain. And that supercooled rain is then treated with this pretty dated emergent freezing of rain process. And so one of the things that I really hope is a key takeaway from this is that we are still making progress towards understanding what the actual aerosol cloud feedbacks are of the Southern Ocean. So that's the sort of bold statement here of Southern Ocean cloud feedbacks, and the role of aerosol remain unknown, but we are making progress through different observations. And piecing together these sort of process studies. And so one of the things I also just want to highlight is that the need for this regime-based, process-oriented, and these collaborative studies, so all these things that we're doing here within CATCH are really necessary to guide model development. And that is really needed for our understanding future climate projections. Because again, like I said, while it is a crazy idea to try to get these microscale processes represented in a coarse resolution model, the fact is that these coarse resolution models are what's being used for decision making and for thinking about the future. And so we do need to have all hands on deck for this. I have two very quick slides, and then I think there's hopefully a nice discussion period. I'm happy to talk more about any of these topics, and I have some extra slides too, but feel free to reach out if you would like to collaborate on any of this. So two very quick slides. It's sort of an advertisement of opportunities, something to look to. If you're a recent PhD graduate, there's a 2-year postdoc fellowship at NCAR through the Advanced Study Program. I did this program many years ago now, but it's a great program, again, a fellowship, so you're able to have a lot of autonomy in this. Applications are due September 1st. And then there's also a faculty fellowship program. Unfortunately, it's only for US universities, but I will also say if you're ever in Boulder, please reach out and we can also host you as a casual visitor as them too. But I just wanted to highlight this as a possible way of collaborating if anybody has any interest in that. So, okay, I am going to, and the application for that closes September 15th. All right, so I'm gonna leave it right there. And I think that was about 30 minutes. So thank you very much.
Thank you so much, Christina. That was really great. Yeah, we can hand over to a discussion. So if anybody has any initial questions for Christina, feel free to raise your hand and unmute yourself. Or if you like, you can also just pop it in the chat and I can read it out loud. Jesse, you want to go ahead?
Oh yeah, sorry. I'm looking at my other screen because I'm having trouble switching it to my main screen. But nice talk, Christina, as always. So I'm just wondering, have you thought of using that? So there's that new parameterization, from Vignon et al. 2021. Have you seen that paper?
For new parameterization for what?
For INPs. And so it's based off of a coastal Antarctic site near Mawson Station.
Okay. Yeah, I have not seen
Yeah, I
that. So
can send
thank
you
you
the
for bringing
paper.
that to my attention. Yeah, that'd be great. Is
Yeah,
it it's just another coastal more along the marginal ice zone?
yeah. So it's based from Marcus data, but only from like 64 south and higher in latitude. So it might be
Yeah.
interesting to look because like instead of just like a straight,
Yep.
log linear parameterization, it actually has some like shape to it. So I'm just curious if you've
Great.
thought of using that. Yeah, I'll send you that paper.
We haven't done that yet, but we do have a project for Cape K. I have some slides, but maybe it doesn't matter. But we do want to try adding complexity because, as you mentioned,
Ah,
this
yes.
marine IMP parameterization, let me see if I can get there. Oh dear. Um, is very simplified. For those who maybe aren't as familiar, this is what I always show for like a summary. It's again still simplified, but the idea is that we know that from the marine sources we have these organic coated sea salt particles, but we also have these microbial types, and these are more active at these warmer temperatures. And we certainly see signatures of that along the marginal ice zone, and of course from Jesse's work in the Arctic. And so right now we're really only representing these molecular kind, and we're kind of able to, I don't know, somehow get away with not doing this, but we need to add that for sure because we do know those exist. So yeah, I will definitely, if you can send that along, we can definitely look at that as part of our project with Carrie.
Yeah, because I'm wondering, yeah, when you get closer to like the coastal regions, like I mean, this was specific to Antarctica, but it seems like for our recent data in the Southern Ocean, like as you get closer to even like Tasmania and Australia, it seems to like fit the data a bit better. So I'm
Hmm.
wondering if it's
Okay,
like more of a coastal marine signature in the Southern Ocean, and it might fit those data better.
cool.
Yeah,
Yeah, that sounds great.
yeah, I'll send it along.
Thanks.
Yes, we have more data for you, by the way.
Great.
Got a question from Jack?
Yeah, Christina, very interesting. I grant your point that, there's a lot of people running these global climate models or 1 or 2 degree models to try to predict climate or future climate, so that at some point you need to get the clouds properly parameterized and represented in these global models. But wouldn't it seem to make sense for you to try to compare your observations to cloud resolving models or at least regional models to make sure you understand the process and then try to parameterize it rather than trying to use
Yes.
unproven parameterization and just stick it in the 2 degree model and wonder why it doesn't work. I
Yes.
mean,
Yeah. Thank you. No, that's great. I appreciate that question a lot. So we are in the process of working on building a framework that does exactly that, which is pulling in higher resolution models where we know the model has a much more sophisticated way of representing these processes. So, for example, we have some low-level cloud case studies from Socrates that we're working on with the CM1 model, which is a Hugh Morrison's high resolution model looking at Lagrangian microphysics. So we're in the process of setting that up. And what we're excited about, I don't know if I want to go into it in too much detail, but we have this project called Inform, which is integrating field observations and research models. And in addition to the course resolution model, that's exactly what we want to do. Is basically we have NPAS, which is our atmosphere for convective permitting model. So NPAS and then CM1, some of our LES scale models are all within that Inform project, trying to figure out how to get all these things together, but also build diagnostics for those so that we can say, okay, we can run this case where we have a really good constraint on our aerosol clouds dynamics and even radiative forcings, you know, and basically tune those high resolution models and then use that to inform what we're doing here. That was kind of a clunky answer for your question, but anyway, yes, high resolution models we absolutely need to partner with, and we're trying. So thank you.
And I just had a kind of a follow-up question if no one else has raised their hand. Not a follow-up, but a different one. I was really surprised when you showed the results early on about how poorly the model was doing with getting sulfur right. And I mean, this happens all the time in the Arctic, right? But there's so many different sources of sulfur there. But
Yep.
in the Southern Ocean, where, you know, probably a lot of it is marine biogenic sulfur, I was shocked that it was so off. Do you have any idea what?
Yeah. I mean, so there's a few things. One is that we're using a version of CAM that has pretty simplified chemistry. There's some recent work now showing improved prediction of sulfate when you have full chemistry in CAM, which has more of these like intermediate species that allow for a better prediction of the chemistry, right? So that's one piece, which is the actual chemistry going on. And again, we have a project looking at Tasmania observations from Cape K that will allow us to have that single particle measurement and help us kind of test some of those parameterizations in terms of improving that chemistry. The other thing that is a limitation of this particular way of running the model, which is like a typical way of running the model, by the way, it's not like I'm trying to be mean to the model. It's a pretty common way of running the model, which is using a monthly climatology. And so that's not really evolving or changing. It's really just sort of a set value over the month. And so, you know, those are two, I think, pretty clear ways in which the model is oversimplifying the sulfur chemistry. And, you know, I think too, I just want to point out that, you know, a lot of times when we're tuning the model, we don't have, in the past, we haven't had a lot of these types of observations included in that development process. A lot of the models will be tuned against things like sulfur, global burden, or more AOD type metrics. And so this is also kind of a first like really intense interrogation of that aerosol. So I think that those are just a couple comments in relation to that. But yeah.
Thanks.
Thank you.
If we don't have any more questions, we have a bit more time left, Christina. You mentioned you had a couple more slides if you are interested in
Yeah,
talking.
maybe I'll just kind of share a recent, or not that recent anymore, new project that we have kicking off. I think this is exciting. Right now, we are focused on low-level clouds over subtropical regions, but the idea is that we want to expand this to include other things too. So kind of what I was just referring to is the development process, how we tune the model, make decisions on changing physics, those sorts of things here at NCAR. And so this is an example of one of those sort of top of atmosphere annual mean, you know, cloud cover bias figures. And this is an example of something that we may look at and make a decision of, okay, we need to change something X, Y, or Z in the model. And in this case, I like this figure because it shows these different, you know, positives and negative biases in different parts of the globe. And so you can imagine that there are different clouds going on in these different regions, different temperatures of clouds, different sources of aerosol, different, you know, there's a lot of complexity kind of hidden in this. And so the idea behind this Inform project is that we're trying to build a process system database The idea being that we have observations that are collected over many different field campaigns, looking at cloud and precipitation microphysics, aerosol chemistry and physics, dynamics, and radiation. What's a challenge is kind of piecing all this together and understanding how they all work, and how to actually use that to compare against something like a coarse resolution model or a higher resolution model. And so what we're doing is basically taking a process system approach. So we're targeting specific cloud regimes. In this case, we're starting with what some people may think is like the easiest, which is this boundary layer cloud regime as we switch from stratocumulus to cumulus, which is like the nice cloud deck versus like pockets and little popcorn clouds. And then we're also looking at tropical convection as the other one, which is of course much more complicated, but a couple postdocs working on this project. And what we're doing is building what's called a process system database. And then we're also building some best practices for how to run the model and how to assess that model. And so this is just showing the low cloud cover challenges that we have right now in the model. So this is specifically looking at CESN2. So this is the satellite record looking at this low cloud type, which is described by a moderate optical depth and a low cloud top pressure. And so you can see this over the subtropical regions. And then when we look at the same cloud type over CESM, we see that we're missing this cloud type. And so this is a known problem in a lot of climate models that struggle with these, subgrid fine processes. But we've had a number of field campaigns that have occurred looking at this cloud type. And so that's what we're aiming to pull together to build that process system database. And the idea here is for this sort of more simplified cloud type. What we are imagining is that we have, this well-mixed boundary layer where we have our stratocumulus clouds. We have some entrainment that as this transitions to this decoupled cumulus cloud type, and we have aircraft observations that sort of probe this system in different places at different times. And so what Ryan's working on is basically developing ways of sampling within that field campaign, different types of sampling maneuvers. So for example, below cloud sampling is needed for getting precipitation or the marine boundary layer aerosol concentrations and composition. So these different sampling maneuvers have to be sort of organized. And then we're doing a compositing. The compositing is basically saying, based on, there's a lot of literature looking at cloud controlling factors or cloud correlating factors like wind speed, temperature, the instability of the boundary layer, and basically being able to say, okay, when we have any measurements, no matter what the type of sampling maneuver it is, if it's in the stratocumulus type, we're going to cluster all those together, and the same thing with the cumulus. And so you end up with this data set that describes all these different components of the system in this one stratocumulus setup, and then in the cumulus setup, and then now you have something that you can assess your model against. So we're in the process of building this. I don't have any pretty results quite yet, but the idea is basically that we have this observation data set, and then we have these different ways of simulating the clouds, in this case with our coarse resolution model, where we can also composite based on that optical depth and cloud top pressure. And then also can even run single column model, which is where we take one column of the model and run that many times with different physics. And then we can do this assessment across these different, this particular type. And then this is where, going back to your comment, Jack, about high resolution simulations, this is another place where we're hoping to build out a lot more of our data, where we have these higher resolution simulations of these particular cases that we can also use to assess against the observation database and also against the coarse resolution model. So that was maybe just to let you guys know on some things that we're looking for are in particular thinking about how to translate this type of framework to the Arctic or to coastal Antarctica, right? This is a very simple, in a lot of ways, a simple process system, but as I pointed out in this figure here, there's a bunch of different types of clouds and a lot of different places that we need to kind of build out this type of database. So that this is sort of a proof of concept for the low clouds over subtropical regions, but we're looking to look out in the future, including the Arctic or some more coupled systems in this. So.
Thank you so much, Christina. Unless we have any final questions, I think we can wrap up there. Yeah, thank you everybody for coming along. Please join us next month for the next Catch seminar. If you want to go back and look at any previous recordings, you can find all of the previous seminars on our website at catchscience.org. So yeah, another big thank you to you, Christina, and thanks everyone for coming.
Thank you for having me.